Hello students, today we will be starting with limits and derivatives and the topic for the day is limits. Before we start discussing about limits, let us study some little bit about functions. As we all are aware, given any function y equal to fx, let us say it is equal to 2x plus 1. So if we have to find the value of this function at any point x, then that value is obtained by substituting that particular value of x in the function wherever it appears. That is, if you want to find the value of the function at any point x equal to a, then we write it as fa and the value comes out to be 2a plus 1. That is, it is obtained by substituting x equal to a in the function wherever x appears. Same way, we can find the value. Here, a could be positive, negative or 0. Okay, so suppose we want to find at x equal to, let's say 2. f2 will be equal to 2 into 2 plus 1, that is equal to 4 plus 1, that is 5. Similarly, at x equal to, let's say minus 3, f of minus 3 would be equal to 2 into minus 3 plus 1, that is minus 6 plus 1, that is minus 5. At x equal to 0, f of 0 is equal to 2 into 0 plus 1, that is 1. Likewise, we can find the value of the function at all points wherever the function is defined. Now suppose we take a rational function. Okay, for a rational function, let's say fx equal to x squared minus 4 over x minus 2. Now suppose we want to find the value of this at 0. What will we get? We simply substitute. We know that this function is defined at all points except at x equal to 2. So for all points, the value can be found out. Other than 2, the value can be found out as, suppose we want to find at x equal to 0. f0 will be equal to 0 minus 4 over 0 minus 2, which is minus 4 over minus 2, which is 2. Similarly, we want to find at any point, let's say x equal to minus 2. Then what will we get? Minus 2 whole squared minus 4 over minus 2, which comes out to be 4 minus 4 over minus 4, which is 0 over minus 4, which is 0. So it is defined at x equal to minus 2 also. But if we want to find the value at 2, then we get 2 squared minus 4 over 2 minus 2, which is 0 by 0 form. Now clearly 0 by 0 is not defined. But in calculus, we want to still carry on further with such functions. We don't want to do away or we don't want to shun these functions at the points where it is not the value of the function is not defined. So in order to come to our aid, there was the concept of limits which was introduced. So instead, like suppose let's take a number line. This is 0, this is 1, this is 2, this is 3, 4 and so on. And here we have negative values. Now instead of taking the value of the function at 2, what we do is we take it in the immediate neighborhood, and by immediate neighborhood, we mean a value extremely close to x equal to 2 but not equal to 2. Now you all may say that the neighborhood like 1 and 3 both are in the neighborhood of 2. No, we can't take 1 and 3, though they appear to be very close to 2, but still they don't form a part of the neighborhood of 2. By neighborhood we mean a value which is extreme, because in between 2 and 3 there can be infinitely many real numbers. Similarly, in between 1 and 2 also, they can be infinitely many real numbers. We want some values which are extremely close. Like for example, we can take some values on the right as 2 point, let's say hundreds of 0 followed by 1, or you can increase the number of zeros and followed by 1 or 2 or 3. This value, though it is extremely close to 2, but yet it is not equal to 2. You can further find a value which is which lies between this value and 2 also. Like you increase the number of zeros, you will get a value which is even closer to 2. Similarly, we could take a value which is close on the left neighborhood, or which lies in the left neighborhood, which will be equal to 1.9999, and hundreds of 9 you could have. You keep on increasing the number of 9s after the decimal point. You keep getting values of x closer to 2, yet not equal to 2. Now let's see how does assuming these values help us. Okay, now if you see that the function is x squared minus 4 over x minus 2, the value of function at 2 is equal to 0 by 0 form, and it is not defined. But suppose we take the limit. Now if you find a value which is close to x equal to 2 but not equal to 2, so then the value of fx so found is called as the limiting value of, let's say, y as x approaches 2. So this is called as x approaches 2 or x tends to 2. So the value of the y so obtained is called as the limiting value, and we write it as limit x tends to 2 fx or lim x tends to 2, or depending upon what is the value to which x is approaching, it may be a in general. So that we write f of x. So here both the things LT and LIM, they refer to the same thing, that is limiting limit as x tends to 2 of fx. You can stick to any one of the ways of writing that. Now, so if I do limit x tending to 2 fx, this will be equal to limit x tending to 2 x squared minus 4 over x minus 2. This, when you solve it, you write it as limit x tending to 2 x minus 2 into x plus 2 over x minus 2. This can be cancelled and we are left with x tending to 2 x plus 2. Here this function, it's a polynomial which is defined at all values of x, even at x equal to 2. So simply we substitute the value of the limiting value of x in place of x, that is 2 plus 2, which comes out to be 4. And so we see that though the value of x at 2 is not defined, limit as x tends to 2 fx is defined and is equal to 4. It is equal to 4. Now you may think that the same procedure we could have done for finding the value also at x equal to 2. But now here this we cannot do. Now let's see how and what is the reason behind it. Now when you find, now fx is equal to x squared. If you write x squared minus 4 over x minus 2, and when you write it in the factorized form. Okay, so this, to be able to, you may think that we could have cancelled it here also. So we can cancel it at all points except, you can cancel it at all points except at x equal to 2. Reason being, at x equal to 2, this is 0 and this is also 0. And you can't cancel 0 with 0. Okay, so even though you could cancel it like this and then you substitute the value of x as 2, you get 2 plus 2, that is 4. That is okay. That is true for all values other than at x equal to 2. Whereas when you are finding the limiting value, in this case when you cancel it, here x is not equal to 2. It is, even though it is extremely close to 2, so that the difference between x and 2 will be either a very small positive number or a very small negative number, depending upon whether x is more than 2 or less than 2. But still, it may be, even though the difference is extremely close to 0, it is not equal to 0, and hence we can cancel x minus 2 by x minus 2 in the limiting case, though it is not possible in the case of the function. And thus we see that this is how limits come to our aid. And if you see carefully, you see on the number line, what have we done? This is 1, this is 2, this is 3. Now if you are taking in the extremely close neighborhood, right neighborhood of 2 or left neighborhood of 2. If you are taking the value as 2.hundreds of 0 and then followed by 1, or 1.hundreds of 9 and then followed by whatever number, then these are, or the difference between these values and 2 is negligible and can be assumed to work the same way as at x equal to 2. And so the further calculations can easily be done by using limits. Now let us understand what is the definition of limits. Now we define, now let's do, this was the concept behind it, and now let us do the definition of limits. Now we define the limit as, now limit x tending to a fx is equal to f of a, where x is extremely close to a, and this is true as far as the function is defined at x equal to a, or you could write it as L, and this is the value of the limit. Okay, so what we do is, for polynomials or for functions which are defined for x equal to a, the limiting value of x is the same, limiting value of fx as x tends to a is the same as the value of the function, or which we could write as L. Okay, whereas it is for the rational functions basically which are not defined at some point, you may have to do something for the where the function is not defined, then limits are used. Their use is used maximum when the function is not defined at a particular point. For all the points for which the function is defined, the limiting value is simply the value of the function at that point. Now let us come to algebra of limits. Now given any two functions fx and gx defined on the real where x is any real number. Okay, now we have to study the algebra. We know that, and here these two are such functions so that the limiting value as x tends to a fx and limiting value as x tends to a gx both exist. Now what is the meaning of limit existing? Limit existing means that if you find the limiting value as x approaches a from the left and as x approaches a from the right. If both the values come out to be the same, we say that the limit exists and is equal to that value. So usually the left hand limit should equal to the right hand limit, and we write it as limit x tending to a minus fx should be equal to x tending to a plus fx is equal to L. Say then the limit as x tend to a fx exists and is equal to L. Okay, so left hand limit is written as a minus. A minus indicates that values of x less than a approaching from the left, whereas values approaching from a from the right, that is from values more than a to a. Now another thing to be noted is that a function which is not defined at a particular point, like the example which we take, the curve will have a break in the flow. Like when you do the tracing, at that point there will be a break in the function. So there will be a break in the function, whatever is the curve of the function, there will be a break here. Okay, so it will not be drawn in a continuity. Okay, so that's a break. So instead of finding the function, so there is no value of x at that particular point, that is at x equal to 2. So we find it in the immediate neighborhood, either x approaching from the approaching 2 from the right or x approaching 2 from the left. Now to find the algebra of limits, what we do, we are taking any two functions f and g such that both the limits as x tends to a, they exist. Okay, now in such a case what we do is, first condition is that the limit of the sum is equal to sum of the limits, that is limit x tending to a, the limit of sum of two functions fx and gx will be equal to the sum of the limits, that is limit x tending to a gx. That whether you first find the sum of the two functions and then find the limit, the value is the same as if you first find the individual limits and then add. Similarly, if you find the difference of the functions first and then the limit as x tends to a, the value is the same by first finding the individual limits and then finding their difference. Now the next one comes as the scalar multiple, that is multiplication by a constant. If you have some constant k times fx, so the limiting value of k times fx is the same as first finding the limit of the function and then multiplying it by the constant k. The fourth one is the limit of the product of the two functions fx into gx, that is whether you first find the product and then the limiting value, the value is the same if you first find the limit and then find the product of the individual limits and then find their products. The same way we have x tending to a fx over gx. So when you are finding the quotient of two functions and then finding their limits, the value is the same as the limit gets split into the numerator and the denominator. But now here an important point is to be noted, that provided this limit exists and is not equal to 0. So here we have to put a condition that provided limit x tending to a gx is not equal to 0, because if the denominator becomes 0 then it is meaningless. So these are the values which we have to, these are the basic properties or algebra of limits. Okay, so before going further, now this is the case which we have to do in detail, and this is the case where limit plays a maximum role, because for all others, since the limit is defined, simply the limiting value is the same as the value of the function at that point. That is in case of limits of a polynomial. If you just consider limits of a polynomials and rational functions. So for polynomials, there is nothing much to be done. It is the rational functions which have to be done in detail. So today we are going to take up only limits of polynomials. Now we know that given any polynomial, let's say a0 plus a1x plus a2x squared plus anx raised power of n. Okay, where an is not equal to 0, so that it is a polynomial of degree n. Now we know that the denominator is always 1. So there is no point of x for which the function is not defined. So the function fx is defined for all values of x belonging to real numbers. Okay, so we are considering real numbers where n is a natural number. Okay, so in such a case, the limiting value of the function as x approaches a is the same as the value of the function at x equal to a, because there is no value for which the function is not defined. And so in this case, it will be equal to a0 plus a1a plus a2a squared plus so on an a raised power of n. This is the value. Okay, and with this we can do the first 5 questions of the exercise 11.1. So let's see exercise 13.1. Now if you just find the first question, what do we have? Limit x tending to 3x plus 3. It being a polynomial, what will we do? It's simply the value of the function at x equal to 3. So it comes out to be 3 plus 3, which is 6, which is the same as the value of the function. Now the same way, if you want to do question number 4, which is the rational function. Now x tending to 4x plus 3 over x minus 2. So though it is a rational function, but the value is like it is defined for x equal to 4, because at x equal to 4, both numerator and denominator are not equal to 0. So we simply find it as 4 into 4 plus 3 upon 4 minus 2, which comes out to be 16 plus 3, that is 19 upon 2, which is the answer. So the cases where the function is defined at a particular value x equal tending to a or x equal to a, the value of the function is the limiting value is simply the value of the function at that point. Okay, similarly we can do the third question, which is limit x tending to 1 pi r square. Pi into x square. So what do we have? X tending to 1, pi into x square. So here it is simply pi into 1 square, which is pi. Okay, so in our next video, we will be studying in detail how to deal with rational functions, and we'll do certain results. Thank you.